All right, let's just jump right in. I want you to picture yourself standing at a super busy city intersection, maybe right around dusk. It feels like total chaos, doesn't it? You've got waves of people crossing the street, sirens somehow weaving through traffic, lights flickering on it. It all seems completely random. But, and this is the key, it's not. There is a hidden order, a kind of secret math that's quietly working all around you. And this quote just nails it. It says that underneath all that noise, there's a set of mathematical habits at work. So cities, whether you're in Tokyo or Toronto or anywhere in between, they end up rhyming. They aren't identical copies, of course, but they follow this kind of universal grammar that shapes how they grow and function. And that's what we're going to decode today. So, what do we even mean by a secret grammar? Well, it's not some rigid blueprint that says, build this here. It's more like a set of invisible principles that kind of nudge our behavior and, in turn, shape the city around us. It's what creates all those familiar patterns you see every single day. To really see this grammar in action, let's zoom all the way out to the macro view. You see, as cities get bigger, they don't just become larger versions of their smaller selves. They actually change in fundamental ways. And there's a mathematical reason why a megacity can feel so incredibly efficient and, at the very same time, so intensely overwhelming. Okay, the principle behind this is called power law scaling. Now, I know, that sounds super technical, right? But the idea itself is actually pretty simple. It just means that when a city's population doubles, things like its wealth or its crime rate or even the number of roads it needs, they don't just double, they change at a predictable, exponential rate. And this creates this really fascinating trade-off between efficiency and intensity. And you can see that trade-off perfectly right here. There are two types of scaling going on. On one side, you've got sublinear scaling for infrastructure. You know, the physical stuff. A city with twice the people doesn't need twice the roads or pipes. It actually gets more efficient with its resources. But on the other side, you get superlinear scaling for all the social stuff. Twice the population creates more than twice the ideas, more than twice the wealth, but also more than twice the crime. This is exactly where that electric, innovative, and sometimes stressful intensity of a big city comes from. Okay, so now let's zoom in from that huge skyline view right down to the street grid. Because if megacities are shaped by these big scaling laws, our daily experience is shaped by something else entirely, network theory. At this level, the city is just a giant network of intersections, or nodes, connected by streets, or links. And the way this network is designed, well, it can have some really surprising and counterintuitive effects on our lives. Which brings us to this kind of mind-bending question. What if you build a brand new, super fast shortcut road specifically to ease traffic, and it somehow ends up making everyone's commute longer? I know, it sounds totally impossible, but it's a real thing in network science. So let's break this down. This is sometimes called Brace's paradox. Look at the steps here. You start with two decent routes from point A to point B. Then, a tempting new shortcut opens up. So what does everyone do? Every single driver, acting completely logically in their own self-interest, takes that new shortcut. And the result? The new path gets so jammed that the entire system slows down and travel times actually go up for everybody. It's a classic case of individually smart choices leading to a collectively dumb outcome. So if one perfect, optimal shortcut isn't the answer, what is? Well, the solution is redundancy. A really resilient city grid isn't like a taut wire, where if you snap it in one place, the whole thing breaks. It's much more like a woven fabric. It has tons of different, good enough paths. It can absorb shocks, it can reroute traffic, and it doesn't collapse. It's all about having options, not just a single best one. All right, let's zoom in one last time. We're going from the street grid down to the sidewalk itself. This is the micro level, where math quietly governs our most personal, everyday experiences in the city. It even explains those gut feelings we get about a place, the ones we can't quite find the words for. For instance, we've all been there, right? Why is waiting for a late bus so uniquely awful? It's not just about the 5 or 10 minutes you lose. There's something much deeper going on, and it can actually be explained by a branch of math called queuing theory. And you can see that tipping point right here on this chart. As long as the system is below its capacity, wait times are, they're manageable. But the moment the number of people arriving gets close to what the bus can actually handle, the wait times don't just get a little longer, they absolutely explode. The system hits a wall, and that feeling instantly shifts from this is fine to this is total chaos. And this gets to a really crucial point. For something like public transit, fighting variance is way more important than fighting the averages.
A bus that comes reliably every 6 minutes is so much better than a theoretically faster bus that's supposed to come every 12 minutes but is always late. That predictability, that lack of variance, is what builds trust, and it removes that mental stress of uncertainty. It's the not knowing that really punishes us.
This math even explains the feeling of a street. On the left, you have what planners call high entropy, which is just a fancy way of saying there's a lot of interesting visual variety. Different storefronts, lots of doorways, different textures. It makes you want to slow down and linger. Now compare that to the right side, low entropy, a long, blank, repetitive wall. It feels boring, maybe even a little unsafe, and your brain just tells you to hurry up and get past it. So let's pull back out one last time. What does all of this math, from the skyline to the street to the sidewalk, what does it all really tell us? It reveals that a city, at its very core, is a massive living calculator of trade-offs. It is constantly trying to balance these competing forces. For one, it's always negotiating that fundamental trade-off between speed and safety. Every single decision about a speed limit or a crosswalk is basically a mathematical calculation, balancing how fast we can move with how safe we feel. It's also constantly weighing the efficiency of that single direct shortcut against the resilience of a more complex, redundant network, one that can actually handle a disruption without grinding to a halt. And of course, it's always managing that classic urban tension between all the creative sparks that come from density and the real logistical challenges that come with distance. Pretty much every debate about zoning or public transit is really just a debate about where we should strike this mathematical balance. Ultimately, when you understand this hidden math, all these weird urban mysteries suddenly start to make sense. You get why adding a road can actually cause a traffic jam, why the shade from a single tree is a legitimate public health tool, and why a street with too few doors just feels dead, and why stores can't survive there. So, the next time you walk down a street that just feels right, you know, the one where the pace is comfortable, the shops are interesting, the wait for the light is short, I want you to know that that feeling is not an accident. It's not just good luck. It's a really complex mathematical proof being solved right there, under your feet. As the source material puts it so perfectly, that sensation of ease is a living theorem that the city keeps proving day in and day out. It's the silent, elegant, and incredibly powerful math that is truly shaping our world.